Hello everyone, welcome back. So in this segment we are going to see again mathematical induction, but we are going to see a different form of mathematical induction. So far we talked about one version of mathematical induction, and we saw how we are going to prove some propositional function using induction. Okay, but this is known as so far we talked about the version of mathematical induction, and this one is known as weak form of mathematical induction. Now we are going to see a different version of that, and this one is known as strong form of mathematical induction. So let's see, we have a propositional function. Sorry. So let's say we have a propositional function Pn that we want to prove. Okay. All right. So the propositional function will be true or false statement involving a parameter n belongs to an integer number. All right. So here we have three steps. So the basic steps says that we have to prove that Pn is true for some initial value of n naught or n0 belongs to integer number. All right. So Pn has to be true for some initial value. Now here the induction step is different. All right. So this step, step 2, this is our induction step. Now this is slightly different than our last mathematical induction that we saw. So in this induction step, it is saying that, let's say we have a value k which is greater than n naught. All right, and the propositional function is true for all value, all L, such that L is between n naught and k. Okay, then that's our hypothesis, and then we can say that pk is true for all n greater than n naught. So what actually we are saying here? So let's use the same concept of ladder. Okay, so our regular mathematical induction, we saw that we have to first prove that we can take the first step. Then if we are at any step, we can take the next step. So that's our regular mathematical induction. Because if we are at any step k, we can take the k plus 1 step. So that will prove that we can go to the nth or any given step. Okay, so that's like a ladder. Now in the strong form of mathematical induction, it is saying that let's see, this is the ladder. All right, let's see, this value is k and this is our value n. All right, and that's our basis value n naught. Okay, or n0. So that's our initial value, and for this ladder, obviously the first step is n1, n naught is equals to, our first step is 1. So that's our first step in the ladder. All right, so in the strong form, we have to first prove that we can take the first step. Okay, then we have to prove that for any value k, okay, for any value k, pk will be true if we can any step here. Okay, any step here which is between k and n naught. Okay, between k and initial value. Okay, now if I can take the step 2, 3, 4, 5, if I can prove any one of them which is between k and initial value, then I can prove that okay, pk is also true. Okay, now that will conclude our induction, that we can conclude that Pn is going to be true for every n value greater than or equal to our initial value. So that's the only difference. That's actually much more stronger form. Okay, so the only difference here is that in the stronger form, we have to assume the truth of the statement for all integers less than some integer. Okay, all right, and then proof for that integer. Now in the weak form, actually we just assumed some of the step is true, and if the step is true, then the next step is true. But in the stronger form, we have to assume that we have to actually know that, we have to kind of know that this statement is true for all integer less than some integer. Okay, and this some integer is k. All right, then we have to prove that pk is true. All right, then we can say that yes, that is going to be true for all n greater than or equal to n naught. All right, so now we are going to use actually one example, and this example we are going to first we are going to prove using regular mathematical induction. All right, and then we are going to see a proof using a stronger form. Okay, so then we are going to prove the same problem. We are going to solve the same problem using the strong mathematical induction. All right, now let's first see the problem, and that's actually our first problem in our textbook, which is problem in the segment of 5.1, this is our problem 1. All right, so let's say we have a couple of envelope. Okay, now we have couple of we are going to buy envelope, but we cannot just buy one envelope. We are going to buy envelope as a set. So I have to buy a set which has either 12 envelope, okay, or set of 5 or set of 12. Okay, so let's say this is a box of envelope that has 12 envelope, and this is a box of envelope that has 5 envelope. Okay, now let's say I want to buy exactly n envelope. All right, and I can and here the condition is the n is going to be greater than or equal to 44. Now the problem 1 is asking that can we really buy that. Okay, so here what it is saying, the propositional function is going to look like Pn. All right, so let's see, I am going to buy the envelope box, which are box of set of 12 or set of 5. Okay, so let's say I'm going to buy m box of 12 envelope. Okay, so m times 12, okay, plus n times 5. All right, so this is the envelope I have to buy, and the Pn is saying that the propositional function here is saying that if I buy envelope like that, I can buy exactly n envelope. So I should actually use a different variable here. Okay, so the Pn says that I want to buy exactly n envelope. Okay, so that's my n. All right, and where n greater than or equal to 44, and I can buy exactly n envelope by using these two box. All right, so let's see, use s times 12 plus t times 5. Okay, or 12s plus 5t. Okay, so what I have to prove here, the propositional function is proving that, so I should be able to make a linear combination of 12 and 5, which will give me exactly value n, and n can be greater than or equal to 44. Okay, so now let's do some research first. Okay, let's actually first do some research and find out that whether this is possible or not. Then we are going to prove that using mathematical induction and the stronger form of mathematical induction. All right, so let's say I want to buy 44 envelope, and how many box of 12 and how many box of 5 I'm going to need. Okay, all right, so I think I can do that by using 2 box of 12 plus 4 box of 5. Alright, so that is going to give me exactly 44 envelope. Alright, now how about if I want to buy 45? Now that should be actually easy. 45 is divisible by 5, so if I just buy 9 box of 5 9 box envelope with 5 envelopes, then this is going to give me 45. Okay, all right. So now how about 46? 46 I can do that by like 3 box of 12, okay, plus 2 box of 5. All right, so for 47 I can buy actually 1 box of 12 plus 7 box of 5. Okay, now for 48 I can do like 4 box of 12. That's it. Okay, so I'm going to actually write it as a linear combination of 12 and 5. So here actually I'm going to write it 0 times 12. I should write it here first, but anyway, so here I'm going to write it 0 times 5. So that means 4 box 12 and 0 box 5. Okay, all right. Now I'm going to actually show you just an interesting development here. Okay, so here let's say just we found out that I can buy, okay, 44 envelopes, okay, using this combination 45, 46, 47, 48, like this. Now am I going to actually calculate all of them just by manually to prove that okay, I can do that, right? Okay, so let me just show you one interesting fact here, what actually we can use. Okay, but we're going to prove that later. Okay, all right. So now if I can buy 44 envelopes by using this 2 box combination, can I buy actually 49 envelopes? Okay, so 49 minus 44 equals to 5. So what does that mean is that, okay, so okay, 49 minus 44 equals to 5. So what does that tell me actually? If I can buy 44 envelopes by using this combination, what I can do just with this combination, just add one more box of 5. Okay, and that is going to give me exactly 44 plus 5. So at the same here, let's say I have I can buy 45 envelopes using this combination. So why don't if I just add one box of 5, that is going to give me 46 envelope, okay, plus 5. I'm sorry, so 45 plus 5, which is going to give me 50 envelopes. Okay, so let's just do that. If I add 44, I have this combination for 44, and I'm going to add one box of 5 envelopes. Okay, so that will look like, okay, 12 plus 5 times 5. Okay, now I'm not going to actually do any kind of calculation in my head. So what actually I'm going to do, I'm going to just use this calculation to find out for the next 5 numbers. Okay, for 49 it will be like that. I'm going to use the calculation of 44 plus I'm going to add one pack of 5. Okay, now with 45 I'm going to do the same. I have here 0 box of 12 and 9 box of 5. So what I'm going to do, I'm going to just add one box of 5, and that will give me 50. Okay, so do the same for 46. I'm going to just add one more 5 box. Okay, I mean one more box of 5 envelopes. So 3 times 5, and that's my 51. Okay, So with 47, what I have 1 box 12 plus 7 box 5, so I'm going to 8, add 1, so that will be 8 box 5. Okay, and that's 52. So do the same for 48. Okay, so 4 times 12 plus, so 1 times 5, that will give me 453. And you can use these 5 row to find out the next 5 row. Okay, because now think that you have 49 envelopes. Okay, just add 1 pack of 5, that will give you what? So that will give you 54. Okay, that will give you the combination of 54 envelopes. And that's how actually for any value n greater than or equal to 44, you know that you can actually buy any number envelopes using this combination. Okay, so you can actually use this envelope distribution, and you can actually just play with them, and you can verify. Okay, so you have to just find out the combination for the first 5, and then using the first 5 you can find out the combination for the next 5. Okay, and that's how you can actually continue, and you will know that you can actually buy any number of envelopes by using this combination. Okay, that's interesting, right? So okay, now that we just did some research, and we saw that yeah, we can do that, but how we are going to prove that? Okay, so we can prove that using mathematical induction. All right, now here we are saying that, so here we are saying that n value has to be greater than or equal to 44. Okay, that means our initial value n naught is going to be 44. Okay, so here one example, you can see that our initial value of n can be other than 1. Okay, because the lowest value of n here we have to consider 44. Right, all right, now we can prove actually the P44 is true. All right, because we saw the combination that we can buy 44 envelopes using 2 times 12 plus let me see, 4 box of 5 pack. Okay, 2 box of 12 pack and 4 box of 5 pack. Okay, so our P of n naught is true. Okay, now our induction step, we are going to assume that pk is true. Okay, so if pk is true, that means I can actually transform k as a linear combination of 12 and 5. Okay, so that means k equals to 12s plus 5t. I can represent k as like this, where s and t both are integer. Okay, now I have to prove that pk plus 1 is also true. So if pk plus 1 is also true, that means for k plus 1 also I should be able to represent k plus 1 as a linear combination of 12 and 5. Okay, where s and t, okay, in this form, where s and t both are integer value. Okay, so that's it. So now let's see, k equals to 12s and 5t. So add 1 with both sides. So this is going to be k plus 1 equals to 12s 5 plus 5t plus 1. Okay, now what actually we are going to do, we are going to just do plus 24 minus 24. Okay, so why actually we are going to do that? Actually here we have 12s, all right, 5t, and from our last discussion you can see that we are not going to do actually anything with the 12 pack. Okay, what actually we can do, we can just add one more 5 pack. Okay, so that's why actually we are adding 24 plus 24 minus 24 here, because 24 is divisible by 12. Okay, so you will see actually why we are doing that. So then we can actually make it like in this form: 12 times s minus 2 plus 5 times t plus 5. Okay, now so here k plus 1 can be represented like this. Okay, s minus 2 and 5 times t plus 5. So t is an integer, so t plus 5 is also an integer. All right, and s is an integer, s minus 2 will be also an integer, but here where this solution is going to work only if s value is greater than or equal to 2. Okay, now if s value is greater than or equal to 2, we can see that here s minus 2 is going to be greater than or equal to 0. Okay, and that means s minus 2 is going to be at least 1. I'm sorry, s minus 2 is, I mean here this coefficient is going to be, I mean either 0 or 1. So we know that, I mean I cannot have minus 1 pack of 12, right? I mean I cannot have minus 1 pack of 12. I can have either 0 pack of 12 or any positive integer pack of, okay, 12 box envelope. So that's why the s minus 2 has to be greater than or equal to 0. Okay, so this coefficient, actually the coefficient of 12 has to be greater than or equal to 0, means the value of s here has to be greater than or equal to 2. And then we can prove that, actually our we can represent, we can buy any number of envelope using this combination. Okay, so we'll be back in the next video, and in the next video we are going to see how we can prove the same theory using strong mathematical induction.